attention up here, please. A couple of logistical things, and then we're going to jump in and just do physics, because that's what we do. So I spent some quality time with a pile of about this much AP Physics stuff last night, kind of getting things put together and put in the right spots. I graded a bunch of corrections that you had done on tests. I graded all of what I think I have for late homework and homework that I hadn't graded. I think from my pile that I am up to date, except for the balance labs that you turned in, I don't know, whatever that day that was, like a few days ago. Do you know what I'm saying? That's the only thing I think that I have not graded. Now, if you look at Power School, it has not been updated. Oh. But I've graded it all, and I'm going to put it in, hopefully today, right? Like I hope, that's my goal. But I just want to let you know that whatever I handed back to you, I have already recorded, and it should be in there. And as soon as I get it updated, I'll let you know so you can double check everything. I just, I haven't, time. That's the one word I'm going to say. Okay. I know that at the end of Liberty Time on Tuesday, there were a bunch of people like, I got this, but more corrections, blah, 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 blah. And I did not pay attention to that. All I did was grade what I had. Okay? So if you still need to make corrections, you need to make arrangements with me to do that. Let me tell you the times that one could do that. Before school tomorrow, after school tomorrow, anytime during the day, because I can get it for you and just set you over there or set you in the study hall room. So that is absolutely fine. We could also do early next week. I just don't want you to put it off because we're getting down to the wire, and it's not a healthy thing for you, and it's not a healthy thing for me. But I know that some people, like, your schedules are tight. I get it. But you need to let me know when you're going to do that, okay? Just so that I know to expect you and all that kind of stuff. Does that make sense to everybody? Does that seem fair? Okay. In terms of our schedule and what else might go into, hold on, this is regular physics. Let me pull up your calendar. Maybe. Oops. So we are, just so that you know, we're going to start rotational inertia today, okay? So we are right on schedule, which is great. And then we're just going to keep cruising. I do not anticipate that there will be any other big things that you will turn into me before the end of the trimester, okay? We have a lab, and this is an awesome lab. This is a good, deep, like, dig-in kind of lab, not like a, one-day kind of deal. And so you'll turn it in, but that'll be probably the first thing that you do for trimester 3. Like, that'll be the first, big graded thing. I'm not going to try and get that done before the end of the trimester because I want you to understand it, not to rush through it. Okay? So I think at this point, unless you're missing something, once I get things updated, that everything should be up to date in Power School. Yeah?
What about a trimester cumulative?
So I mentioned this on some other day that you weren't here. My big picture decisions that I want to get you ready for the AP exam. And it doesn't feel natural to me to take a break from this unit to do that. So we will have a cumulative exam. It will probably be, it will certainly be sometime before spring break because that will feel like a more logical break. So we're going to get through this and then we'll see about that. Okay. Does that make sense? Yeah. And we'll look at what that'll look like later and all that. Yeah.
So no final test this trimester?
No final test this trimester. Yes. People seemed okay with that when I said that a couple days ago. Yeah.
When is spring break?
Middle of March.
So
Yeah. Does that make sense? So sometime between now and then. But I'm not going to just be like, hey, it's time, right? Like, I'll let you know, but it won't be worry about your other finals in your other classes and just do physics with me. Okay? All right. Cool. Okay. Other logistical stuff here. So I sent you an email yesterday morning. Did I send you some more problems to work? Maybe I did, some more kinematics problems to work. And I think they had answers on them, if I'm remembering right. There was one that had mathematical and the rest of it was just ranking task stuff. So we can go through that if you want, but that is all on you guys now. You got that? That's yours to do. Hold on just a second. Let me just say that all out loud. And then there's some homework. That's all I asked you to do because that's honestly, we were just going to do a bunch of kinematic stuff in class yesterday. So it's kind of if you're going to have a snow day, this is a good day to do it for AP Physics at least. And so we're going to jump in and do Newton's second law today after a couple of questions that we talk about. Yeah.
So, did you guys learn about, or did we learn about the kinematic stuff on Tuesday?
We did.
Okay,
Yep.
is that on YouTube?
It should be.
Okay.
I think that I have updated everything, but if it's not there, then send me an email. Yeah. I think it's all there, but I'm not going to say 100% because that's how life goes, right? All right. So I wanted to. Would you like to go over those ranking tests that I sent you yesterday? Would that be helpful?
Yeah.
Yeah. All right. Let's do it. We're going to start. No, is it this one? Did you do this one already?
Yeah, it was that one.
That one? Okay. Oh, there we go. All right. So take a look here. We're going to do this fairly quickly because we got lots to do today. So, situation. A pulley and a weight. Angular velocity time and acceleration time graphs. Velocity versus time and acceleration versus time graphs. A weight is tied to a rope that is wrapped around a pulley. The pulley is initially rotating counterclockwise, pulling the weight up. Okay, so somebody must have pulled on it or did something to make it do that, right? So it wouldn't naturally just do that, but it's going up. The tension in the rope creates a torque on the pulley that opposes the motion. The weight slows down, stops, and moves back down. Have you seen something like this in translational motion before? Yeah. Right, you with me there? Same thing as a frog flying in the air, except now it's because of a torque instead of just a force, okay? Part A says to graph the angular velocity versus time for the period from the initial instant shown until the weight comes back down to the same height. Take the initial angular velocity as positive, and then graph the angular acceleration for the time at the same period, okay? Why don't you talk to your table mates real quick about that? See if you've got a similar answer. I'll get you some boards so you can write it out. It might be faster that way. Say. All right. Let me see your boards. You guys flipped them around. I got confused. All right, let's take a look at this. So the question is not only, okay, that seems fine, but how do we know? So I see a lot of this. Oh, that's supposed to be a straight line. I'm not doing a good job with straight lines today. How do you know? Get us started, Nick. How do you know?
Velocity starts positive.
Okay. Okay.
And then after a while, it's going to stop and then start rotating clockwise.
Okay.
And basically, the graph ends when the weight thing returns to its original place, and so like there'll be it's like the displacement. There's no displacement, and so like the net velocity will be 0. But for the first half, it's positive.
Yeah. You could do the area under the curve, right? The area between the curve and the axis. Yeah. Do a little anti-derivativeness, right? This one and this one have to be equal because the total displacement would be 0. That's absolutely fine, and that makes good sense. Yeah. Okay. Why is it a straight line and not curvy or something? Okay, I heard lots of, but somebody raise your hand and tell me. Tell me why. Yes.
Constant acceleration.
Why is it a constant acceleration?
Gravity is a constant.
I like it, like, duh. But let's talk about really, really why that is. And this is going to lead us into our conversation for today. Gravity is a constant, right? If you were going to draw a free body diagram of this thing, right? You got gravity pulling down and there's tension pulling up, but the thing that's really making all this happen is gravity, right? Gravity's pulling down. It's causing this thing to accelerate. Absolutely. And we'll talk about why that is true, because this is not A. Is this? What is this? That's alpha. What is alpha again? Acceleration. Oops. Angular acceleration. Whatever. All right. Angular acceleration, which is talking about how fast this thing is rotating. This thing is rotating translationally. This thing, the pulley is rotating angularly, right? Yeah, it's not like going up or down in translational motion. Okay, so then we had this one going down like this. So the game is, friends, this one has a constant negative slope, right? Constant negative slope means constant negative values here. Does that make sense? It's the same game that we did before. So the thing that I want you to remember, we spent a lot of time when we were doing translational motion. We had that chart with like those 9 graphs. Remember we did the DVA graphs with all those different situations? You could take that to a copy machine, make a copy of it, and every time you see a D, you could change that to a theta. And every time you see a V, you could change that to an omega. And every time you see an A, you could change that to an alpha, and you would have the same setup for rotational kinematics as you do for translational. It's the same stuff, okay? All right, we're going to come back to this concept in just a minute. I wanted to look at the other problems that it gave you here. There was this one here that said, the figures below show, hollow spheres not drawn to scale that are rolling at a constant rate without slipping. The spheres all have the same mass, but their radii as well as their linear angular speeds vary. It says rank the radius of these spheres. How are we going to do this? Do you want to talk about it for a minute?
Yeah.
Okay, why don't you talk for a minute, and then we'll go. Isaac, what's the matter?
No, it's fine.
Oh, okay. All right. So here we go. Before I ask you your answers, I want to make sure that we're understanding where this is all coming from. Because you're not feeling good? This is something that I don't think that we actually articulated on Tuesday, so I want to make sure that we can figure out a relationship between translational velocity and rotational velocity. What is the relationship between translational and rotational velocities? There's a really nice, lovely way to do it. What is it?
Well, in the book it mentions velocity equals radius times.
It does mention that. Now, if you read it in the book, that's awesome. That's cool. I want to make sure we understand why that's true. So I'm going to actually go back to our notes from before because I realized that we didn't actually articulate this per se, and I want to make sure it really, really makes sense to you. We talked about what a radius or what a radian is. Do you remember this? We talked about what a radian is, and we said it, but we didn't really write it down. So I want to write it down right now, okay? So we've got an angle theta, and I told you that the angle theta was the ratio between the arc length and the radius. You remember that? So I want to actually write that down, like explicitly right now. So theta is equal to the arc length over the radius. Not liking denominators, we could say that x, the translational displacement, is equal to theta r. Okay? And that is true always. That's something box-worthy. That's something that's really nice because anytime that you have an object that's moving in a circle, if you want to know how far it's gone translationally, just multiply the angle that it's swept out times the radius. Boom, you're done. Okay? This is not magic. This just literally comes from the definition for radian. That's all it is. Okay? The nice piece about this is that we can use this then to define all of the others as well. So I'm going to do that on the page that we were just on here. So, oops, not that one. It was this one. I'm going to go down here a little bit though. So we just said here just a second ago that displacement is equal to theta times r. We can do the same thing for any other version. So like, I don't know, maybe for velocity. We know that velocity, just basic definition from 500 years ago, not literally 500, maybe a few months ago, was displacement over time. But we can say now that this is theta r over time. Are we okay? No monkey business, friends. I'm just showing you how this works out. Okay? So then, hey, what's theta over t? Omega, right? Angular velocity. Theta over t. Is that what you said?
Yeah.
High five to you. Nice work. Yeah, you got it. So there we go. So we can say then that translational velocity is equal to r times omega, or omega r. Boom! If it works one time, I bet it'll work the other time, but let's write it out just so we make sure we believe it. A is equal to change in velocity over time, yeah? This is really nice. It's really clever because we know that velocity is omega r. Then we got that over t. And then I'm going to ask, Henry, you ready? Oh,
That's all right.
that was the wrong answer. Come on. What's omega over t?
Angular acceleration.
Boom, there you go.
I'm on fire.
He is on fire today. So we can say
I'm fully gay.
Sick joke.
these would be box-worthy things, okay? Glitter pen-worthy things. Highlighters and stars, stickers, put it all over. These are good things to know. Laminate it. Just that little part in your book. I don't know, whatever you need to do so you can see that. Wow. Speaking of marketing, right? We got this. I need you to do some marketing for my physics. There we go. Yeah, that'd be good. All right, here we go. Oh, I'm not going anywhere.
Just hold on.
That's a fish.
No.
Iceland.
It is the letter alpha.
No, that's sort of
It's the first letter of the Greek alphabet. It's right there. That's the last time you say that. Just saying. I feel strongly about this. All right. So help me out with this. So Nick was feeling resourceful, so he found this. But now we all believe it, right? V is equal to r times omega. So if this problem was hard before, hopefully it's not super hard at this point. Does that make sense? Do you need 5 seconds more, or are you feeling good with your answers? Show me your answers. What you got?
Wait, so what's omega equal to? Omega is equal to radians.
Omega is radians per second. So you got radians per second times meters is going to give you meters per second.
So omega is radians.
B, oops, I said B and wrote C. Go me. B, C, F, D, E, A. I'm just writing this down. I'm not saying it's right. I'm just writing it down to see what we do, so we compare. That's right. You said B, C, D, F, A, E. Boom. What do you guys have? Do you have this? Or just something different?
Yeah, that's not the same.
Yeah, it's just a different order.
That's right.
They just didn't do enough alphabetical order. All right, are we good? I want to keep going. Okay, I'm going to keep going. This one, shh, friends. I'm going to leave this. If you have questions about this one, the solutions are here. If you have questions about this, let me know. We can go through it another time. It's just kinematics. Remember, at the end of class that day that we were doing all this, that was what, Tuesday? We wrote down all of our kinematics formulas. You just read the other ones and then you change them, right? Just change the letters. You're done. Okay? I'm going to give you another one to look at right now. Here it is. It's a lot of words because it's kind of interesting. Black hole, which is named GRS 9 or 1915 plus 105, whatever, right? Is in the constellation Aquila, and it's about 35,000 light years from Earth. It's kind of a little ways away. So that means that the light from the things that are orbiting it have taken 35,000 years to get to Earth. That's kind of a long time. I'm just saying. Okay. It was formed when the core of a star with about 14 solar masses collapsed. The boundary of the black hole is called the event horizon. It's a sphere with a radius of 25 kilometers. So think about what I just said there. There are a lot of words, but I want you to understand what this is saying. 14 of our suns, 14 solar masses in something with a radius that's only 25 kilometers. That's a very, very dense object, right? Very, very dense. All right. Surrounding the black hole is a stable gas cloud with its innermost 30-kilometer radius stable circular orbit. So things inside that are not stable because at 25 kilometers you go whoop, in. There you go. This cloud moves in a circle about the black hole. So this cloud of dust and gas that's orbiting the black hole orbits 970 times every second. 1,000. It's gone around 970 times.
Around 25.
Okay? I want to know the tangential speed of that dust. Go. Fast is the qualitative answer. I want the quantitative answer. How fast? Hold on, friends, can you be quiet for just a second so I can hear the question? Yes. Yes. Good word. All right, give it a shot. Okay. So I'd love for somebody to talk me through this. Don't just tell me an answer, because for friends that don't know what they're doing, just an answer is not going to tell me anything. So talk me through how to deal with this problem. I don't think we need those values. I think we just need really just that stuff, right? All right. So how might you approach this question? Oops, go away. Not you, the thing. Sorry, I realized as you walked up that may have sounded bad and I didn't mean it that way. All right. Nick, go for it. Do you feel like that's all you're telling me? Because that's the last thing you said to me. So velocity is radius times omega. Okay, keep talking.
It says most of the radius in meters would be 30,000. And to find omega, you need to, it gives you 970 revolutions per second. So
Friends, I would really appreciate it if you could be quiet for a couple of reasons. Number one, it's just rude to talk when other people are talking. Number two, I am recording this because I do have people that are gone and I need to make sure that they can hear it, right? And it's just distracting to everyone. So for any one of those three reasons, please be quiet. If you need to chat, then just chat really quietly. Yes?
you have to convert revolutions to radians, and you just multiply 970 by 2 pi. And so that's how many radians and kelvins per second. That's the angular velocity.
Does that kind of make sense? So a lot of this is dimensional analysis. I know in chemistry they love dimensional analysis. And in this physics stuff, when you're really not sure what to do, always going back to the units, they will always, not always, almost always lead you to the right thing, right? At least the right idea. So we got revolutions and revolutions on the top and the bottom, so those are going to go away. Remember I said that if you're dealing with radians and there's other stuff involved, the radians just poof goes away because it's really just a ratio of two distances anyway. So the radians don't matter. So now I've got something in meters per second. So I know that I'm on the right track, right? I know that I'm on the right track. Then I just need to plug stuff in. And when I plug in numbers, what do I get for my velocity? In meters per second. Fast is the qualitative answer. What's the quantitative one? I didn't hear that. What?
Okay. 182,840,692.4 meters per second.
Okay, can you write that in scientific notation for me?
1.8 times 10 to the 8.
Yeah. Okay. So, fast?
Yeah.
Yeah. That many meters per second. Now, is that too fast? What do I mean too fast? Faster than the speed of light. So this is another one of those top tips, right? When you're doing math and you're like, I'm not sure if this is right or wrong. If you get an answer that is greater than the speed of light, it's wrong, is the short answer there. The speed of light is how fast we did it before. Do you remember? Okay. So if you get something bigger than this, there's a problem. This is almost 2/3 the speed of light though, right? So yeah, that's fast. Yeah, that's pretty good. That's pretty fast. Whee! It's pretty fun. I want to know, just by comparison, real quick, could you tell me how fast is the Earth going around the sun? In fact, I'm going to ask you all to calculate it.
2 pi radians per year.
Fast is the Earth. That was awesome. What do you need to know? Do you need any information from me?
So, the radius of the Earth is no, just astronomical units.
One AU, friends. 1 AU is the distance from the Earth to the Sun, right? We're very selfish and we like to define things that make sense to us. That's 1 astronomical unit. So when we're talking about things really far away, sometimes we talk about them in terms of astronomical units. But 1 astronomical unit is equal to 1.5 times 10 to the 11th meters. Okay? Now you know everything you need to know. Figure it out. How fast is the Earth? That's what this thing means. Traveling around the sun.
Yeah.
You look unhappy. What's wrong?
Wait, 1.5 times 10 to the 4th is the distance from the Earth to the Sun.
That's 11. That's an 11.
I was like, that's way. I thought it was.
No,
small.
yeah. That would be very much too
That'd be
small.
very small. I was like, that's only like 15 kilometers.
Yeah, it'd be a little warm. Be a little warm. How are we doing? You're doing the same process, aren't you? So you need to do it. I want everybody to do it. No excuses now, friends, because we just did the other one. How fast is it going? How fast?
30,800.
I got 2.9 times 10 to the... That one's a 4th.
Yeah.
It's on phrase.
I know. Thank you.
This by.
So we're going a little bit slower. Now, it's still pretty fast, right? It's still pretty fast relative to, like, I don't know how fast I can run. I don't know. But it's a lot slower than that dust going around. All right. We have got 6 minutes for me to introduce some new information to you. So, clear your brain, take 1 deep breath, and then, that was really nice. We're going to do some more translational versus rotational. We have to do Newton's second law today. I teach you Newton's laws as Newton's first and second law all together, but we kind of split them into 2 this time, okay? So, Newton's first and second law, really, the way that we've learned it, that if F net equals 0, then what?
Torque is no. Equilibrium. It's equilibrium.
It is equilibrium, which means the acceleration is 0. And if F net does not equal 0, then what? Awesome. And in fact, not only do we say that, but we also say that we know that the acceleration can be calculated if we know the net force and if we know the mass, right? That's Newton's first and second law in translational language, okay? Let's do the other one, though. So I'm just kind of continuing my chart. Not sure if I told you that before. Sorry about that. Sorry. Okay. Let's write the rotational equivalent. So, Henry, you were just there. You were just saying it. If, what am I going to say instead of F? In terms of rotational, what is the rotational equivalent to force? Torque. If the net torque is equal to 0, then what do you know? It's at equilibrium. That means that alpha is equal to 0. And to complete that statement, if net torque does not equal 0, then what do you know about alpha? Hot diggity, you got it. There you go. Newton's first and second law in terms of rotation. But there's that one little piece that needs to go down here, isn't there? So here's the thing that we got to figure out. We're going to say that alpha is equal to torque net over something. But that something's going to be a little bit different. We need to figure out what that something is. So we're going to do that right now. I think we can do it. I believe in you. I believe in me. We got it. All right, here we go. All right. We know that A, well, what's that? Lowercase. I mean, it's the curly one. Yeah. I'm going to write this as A times M is equal to F net. Bless you. I'm going to multiply this by R, and I'm going to multiply this by R. Am I allowed to do that? Sure, why not? What's F net times R? Torque. Is equal to, okay, so we've got, oh yeah, I guess we could do this. We could say R times, oh, instead of A, we could write this as alpha times R, right? Yeah. Times M, are we okay? I haven't done anything too mysterious there, right? All I did was multiply these to get that. And then I just translated my A into its equivalent. Its equivalent is alpha R. We proved that earlier today. And now, oh, this is kind of cute, guys, because now we've got two R's, don't we? Two R's make it R squared. Ah. I didn't hear you. I'm sorry.
What did you say? 2 R's make a pirate.
That wasn't funny.
And you go to the hall.
Yeah? Are we okay? No? Why not, sweetheart? Talk to me.
We thought alpha was equal to A, not AR.
No, alpha and R are equivalents. One is in translational, one is in rotational. But they're not the same value. Does that make sense? And earlier when we were doing that ranking task, we said that if you know alpha and you know R, you can find A. Alpha times R is A. Is that okay? You can say no, and that's okay with me.
It is.
Angular acceleration. So this thing has a name, and I want to write it in here. Usually write it as mr squared. M is just mass, right? This thing has the weirdest name of anything you're going to learn about this unit, at least, if not this whole year. Here it comes. Write this down before the bell rings. Moment of inertia. Why they gave it a 3-word name, I have no idea. Why they make it sound so scary, I have no idea. But tomorrow we'll go through and talk about what moment of inertia is, and you won't be scared of it anymore.
This is why nobody likes Isaac Newton.
Please make sure that all of the whiteboards and the markers get put back in the drawer before you go. All right? Bell's going to ring in like 10 seconds.
James got it.
Yeah, exactly.